Hello, everyone, and welcome to the Module 4 Python exercise. In this notebook, we're going to be going over support vector machines at the very end. But the main goal of this one is that I want to walk through a classification problem end to end. Earlier, the previous modules, and especially last module when I just did not have the internet to record a video, I noticed we were approaching problems in small pieces. So, looking at things just kind of in a silo. And I wanted to take the time in this video to walk you through exactly what I would do with a brand new problem. I have not looked at this data set before today. So, I created this notebook today for you all to just kind of see this is my thought process for everything. And just kind of to note on that, since I did create this today, this is not going to be a perfect walkthrough. This is not going to be the most genius thing you've ever seen, but this is a realistic view of what I would do given a brand new data set and knowing that I want to focus on classification problems. So with that, we are going to be working with the HEART data set from the UCI machine learning repository. So I left the documentation here and it's just right here. You can see I was looking up what some of these things mean. So UCI, it's the UC Irvine Machine Learning Repository. We've gotten a lot of data from them this semester, tons of great information. So you see the data set, and the original data set had 76 attributes. The one we're going to use only has 13, so they've narrowed it down a little bit. You see the variables table, so the variable name, role, type. Some of them have descriptions, some of them do not, so I had to look up some of that as well. This is a very normal data dictionary for a company that would be very organized. So if you got this in the workforce and you had tons of documentation and you were able to look things up like this would be a really great environment for research. In most cases, you are given a data set or realistically access to a database, and you have to find this all out on your own. In this case, we're really lucky and they've already narrowed this down for us. So even though we are not in the medical field, we know in general that we're looking at heart disease, and we know that these factors probably cause some sort of heart disease. So it's just kind of a preamble to know that even though we are starting from scratch, we're not really starting from scratch in this kind of environment. So yeah, we're starting off in a pretty good place. If you read through some of this, you get a lot of clues. So when you're looking at assignments and you feel a little bit lost, always go back to the data set. So for some of this, it looks like a 0 for heart disease means that there's no heart disease. And there's actually integer values, 1, 2, 3, and 4, to say that there's some sort of disease. But in a lot of the classification problems that were going on here, they were really just looking at, was there a presence of disease or was there not? That's going to come into play later. It looks like there's been a lot of ML researchers looking at this kind of data set, but really only a subset of the variables have been useful. So they've already subset a lot of this for us, which makes it pretty nice. And on this website, I've noticed you can download the data set, but I've figured out it's way easier just to import into Python. And since we've already done this installation, and I've shown you in the notebook exactly how to import the data set into our code. So with that, we're going to import our packages, the same ones that we always do to start, pandas and NumPy, whatever you want to call it. And then we're going to get our data set from the UCI repository. So we're just going to get the data set, and I just called it heart. The ID is 45, so that's what I got from over here. And they have already taken the data set and said, this is our X, this is our Y. I want to start further back and just look at this as a data frame. So that's why I've taken that X and Y, and I've just combined it into, this is my data frame. And I'm just going to pause this for a second. It's not a real recording until I have to pause it to let a cat out of my office. So we've got our data set. You see the num that is there heart disease, and remember a 1, 2, 3, or 4 means that there is, a 0 means that there's not. Age, sex, and then a lot of variables I don't understand because I'm not in the medical field, but that's why we have our data dictionary. So some of the cleaning and preparation, again, because we want to reframe that data set and it's the data dictionary already told us that it's okay to do this, we are going to change that presence of heart disease. And instead of the 1, 2, 3, or 4, we don't want to predict if it's a 3 or if it's a 2. We just want to say, does someone have heart disease or do they not? So to do that, we're going to say that DF num. We're doing it this way because I don't care if we lose this variable. I don't need the original. But if you wanted it, you could change this to binary so you don't change your variable. I'm using that num. No, I'm just going to go with numpy. That's what I'm going to call it. Numpy.where. So tell me where this column is greater to or equal to 1. And if it's that, just recode it as a 1. If it's not greater than or equal to a 1, let's say it's a 0. So that should go 0, 1, 1, 0, 0. So that's what we should be looking at. And we can double check that that worked by just doing a quick df.head. Let's look at that beginning. Oops. Perfect. So just like I said, we should have 0, 1, 1, 0, 0, 0, 1, 1, 0, 0. Perfect. Okay, so that worked exactly like we wanted. I noticed a few of you had issues with this kind of statement, and it was because you were putting quotation marks around this value. We only need that if it is a string value. Unfortunately, the very first example I did was a string, and then the rest have been numeric values. So if it's a number, you just need the number. All right, and now, like I said, that week 1, that module 1 where we did exploratory data analysis, you should be doing that with every data set that you get. We're not going to go into a ton of detail in this one because this is just a practice one, but this is my typical, I've never seen this data set, let me figure out what's going on. I'm going to start with that describe function. Tell me what's going on. I know that num should be between, or it should be 0s and 1s, so this column's not really useful to me. Let's see, age, okay. Average of 54 years old, that makes sense. Minimum 29, okay, that's making me feel a little bit nervous about my heart. Maximum of 77 years old. Sex, it should be 0s and 1s. And then the data dictionary would tell me which one's a 0 and which one's a 1 somewhere. I'm not going to dive in right now, but it's there. All of these other values are there. The biggest thing I was curious about is I know some of these are categorical and some are numeric. So like this one, I wanted to see, are these 100 values cholesterol as well? Are all of those going to stay pretty high? And yeah, okay. So the cholesterol, whoa, that's pretty bad. That, yikes. Okay, so that goes up pretty high, and you see how that scales. So it goes from 126 to 564. This one goes from 94 to 200, where something like CP goes from 1 to 4. And I believe that's a categorical variable, if I remember. CP, yep, categorical. So we need to remember that later. Once we need to start building our model, we have to think about, do we want to normalize our data or do we not? Some of the other ones, some things that stick out. Again, this one, I know it's a categorical just from looking at the data dictionary, but also I can see very clearly it goes from just 3 to 7. This one goes from 0 to 3. So again, we're looking at some columns that have a much wider scale. So cholesterol versus some of these, again, not a medical person, but these are very, very different. I believe this was the presence of a specific heart occurrence, something, either 3 or 7, maybe 3, 5, or 7. So it's just they're on different scales. We're going to have to remember that when we're modeling, because remember, some of our models are very sensitive to that. Think the logistic regression versus our decision tree that is not very sensitive to that. Let's start looking at these in a different way. So I love correlations as a place to start. That's not the end all be all. And I showed you in that homework 1 solution, you can look at the correlations of all of it. And if you want to make it a little bit prettier to make it easier to see. So the ones across there, you're always going to have a 1 because num is always going to have a perfect correlation with itself. But then you can start to see the other things that stick out. So this variable, of what I'm just going to start pointing at things. I don't know what these mean. It has a lot of negative correlations with some of the other variables. I start to notice that the presence of heart disease has some positive correlation with CA and THAL, although I will go into it in a minute, but those are some of the categorical variables, so that's not 100% something we should definitely look into. Yeah, those are the first things I see. So look at my really negative ones, like the consistently negative ones, look into the ones that have a couple positives with my target variable, and let's just start plotting them. So let me look at the heart disease versus THAL. That was that one that had the positive correlation. And you see my issue here. So heart disease, either it's 0, I don't have heart disease, or 1, I do. And this is my categorical variable. It's either 3, 6, or 7. And you see the issue. So there are about 300 instances in this data set, and I can verify by saying df.shape. Okay, so there are 303 rows in this data set, and there are 6 points on my scatter plot. This means there are a lot of repeats, so a scatter plot like this does nothing for me, which also means that correlation is not going to help me whatsoever. So that's always good to know. Always just look at your data, see what's going on, because sometimes it's not actually going to help you. Let's look at another one to kind of demonstrate that. So this one, I'm at least seeing a numeric value. This is the old peak. It's, I think, the maximum heart rate at a certain point. Yeah, max heart rate. I did a good job labeling versus that heart disease. It's still binary though. So remember, a lot of you were creating those scatter plots. These are really good to look at still because you can still start to notice a pattern. You'll see that the max heart rate is slightly lower. Oh, that's actually interesting. It's slightly lower for those that have heart disease versus slightly higher for those that don't. Interesting. But since it's binary, correlations aren't going to do us a lot of good here. The scatter plot doesn't show us anything. You'll notice it's not something we could put into a linear regression. But this gives us a little bit of insight into just what's going on with our variables. Versus this next scatter plot is something that you should use as a scatter plot. This is a very typical one. So we've got 2 numeric values, maximum heart rate, ST depression, and we can start to say, is there a pattern? And here I would say, not as much. No, there's a higher concentration of no ST depression in this heart rate range, but yeah, so less of a pattern. So not every scatter plot, not every correlation is going to tell us something, but it gives us a little bit of an idea of what's going on in the data and maybe some things we should look out for. My next step is, are there any missing values? So is there anything I should know about? And I see very quickly that the only missing values are with these 2 variables. So I can look a little bit further and see, okay, what's going on here? Let's look at when CA is null. So give me the data set, but only when the CA is null, and let me see those rows. And you see what it was saying here. So this column is null. Okay, and then let's look at the other one. And unfortunately, these do not overlap. I was hoping maybe these 4, these 2, maybe there was some overlap, but these are all separate. And as I point out here, because these are categorical, I can't add in just let's take the average. It's not like it's age or cholesterol. I can't just plug in the average. Because I'm looking at this and it's a mix of heart disease and not heart disease, it's also, it gives me pause. Should I throw out the data? Should I keep it in? I'm a little worried because I wonder if these values are actually really important. So my gut instinct is I'm going to take these out. It's only 6 rows out of 303. I just have a feeling I'm going to need these later. They're gonna be important. I'm gonna take them out. If it was more than that, I would think about maybe should I just remove these columns and not use them? But because I have a feeling I'm gonna need them later because of what I was reading over here. Major blood vessels colored by the fluoroscopy, that's really important. This one was an indicator of some sort of heart thing, not disease, but something they can see in your heart. So I'm thinking I need these columns to be filled out. I need that data. I'm going to take out those rows. And to do that, I can just say, take my data set, drop the rows where it's NA, and in place equals true means do that here in place without me having to redefine my data set. And now when I rerun this, are there any null values? No. And then lastly, before we build any models, let me just look at my data set. And you'll notice that this is a little bit more balanced than your wine data set, so that's nice. There's still more of that zero. There's more of the negative. So there's more people without heart disease. That's very, very common when you're doing classification models. You're almost always going to have more data on the thing you're not looking for, because otherwise, why would you be looking for something if it's very common? So if everyone had heart disease, why would we ever make a model? We would just treat everyone for heart disease. But because it's a little bit more difficult to find, that's why we have a job. That's why we're looking at data. But it's at least more balanced. We're probably not going to run into as many issues as with the wine data set, where you had that imbalanced class problem. Your model was really good at finding bad wines, but really bad at finding good wines. So hopefully that's not an issue here. So at this point, we know a few different classification models. You know logistic regression, you know decision trees and random forests, and then hopefully you've watched the piece on support vector machines and you're going to try that out today. So we are going to do all of those, and I want you to compare and contrast. So take some notes on what you get for the accuracy, precision, what type of evaluation metrics you think you should use, and let's see if we come to the same conclusion at the end. So to start off, I'm just going to say, give me my columns because I need to redefine that X and Y. Since at the beginning, X and Y were defined, but I changed that num variable a little bit. Let me just redefine it. And I said df.columns because that allowed me to just take these and copy and paste. One thing I did see on a few people's homeworks is when you're defining X and Y, you have to make sure a few things. First, Y is your dependent variable. It depends on your independent variables. So it's the thing we are predicting, it's our target variable. And in addition, that target variable cannot be in your X variables because at that point, you're essentially giving your model the answer. And you will get 100% accuracy and you're going to wonder why. And it's because you gave it the answer. Now, I've added a little note here. Should you normalize your data? And unfortunately, there's no rule for, yes, you should always do it, or you should do it in these 3 instances. That's a lot of the answers in data science is that maybe. My answer is always, it depends. So should you normalize? It depends. I know in this data set, I will get an error with logistic regression saying that it couldn't split the classes. So I know I needed to add some sort of normalization in here. So the fact that I have this in here means you should. But I do want to say, do not normalize your data and save over your data set. So do not get rid of your original data set. You're going to need it. And I honestly recommend normalizing your data set and trying it both ways because you might be surprised what works and what doesn't. So I'm going to start off with this min-max scalar. And you'll notice here when I'm splitting my data set into the train test split, I'm just doing it twice, completely normal and then the other way, the scaled one, just so I can keep track of everything. So logistic regression. Remember what we learned, that that one needs numeric values. It is sensitive to outliers. It is sensitive to those non-normalized values. That's why I knew it needed the normalization. We're essentially leading ourselves towards a linear relationship without needing a strictly linear model. Because remember, this logistic regression is built on the linear regression model, the same sort of mathematics, but we've turned it into a binary problem. So to do this, we're going to say, give me my logistic regression, fit it to my scaled model. You will need that numpy.ravel to fit it here. And then let's try it out and see what worked. Oh no, I forgot to send something in. Oh, and this is the problem with cells. I ran things out of order, so I did not have this metrics in. So let me make sure it is here now. No, it's still not. Where is it? Here it is. Okay. This is why I run these before I give them to you. There we go. Okay. Ooh, accuracy score of 0.9, so 90% accurate. I can take in a row of data, so I can get an instance of a person, and I can say with 90% accuracy if they have heart disease or if they do not, which is, as my old boss would say, creepy but cool. Let's see what this looks like. So here's my fancy way. How I look at this, a couple of you had problems with this. Always follow V's, and it's a matrix because it's rows and columns. If that gets confusing, just always go with, here's what I predicted and here's what was true. I predicted heart disease, and it was true in 22 instances. I predicted 1 and it was 0 4 times. And this is the one I was worried about. I predicted no heart disease, and there was heart disease only 2 times. So that's actually pretty good. That means I am missing very few instances of heart disease. And the full classification report. So again, the accuracy was 90%. And remember to look up the evaluation metrics. They're on the required learning activities this week. But if you look at precision, recall that F1 score. I want these, at a glance, I want them to be kind of similar. In this specific problem, I want to make sure my disease is optimized as possible. So I'm not as concerned with my accuracy rate. I want to make sure none of these values are dipping low. So I'm actually pretty happy with this. It'd be nice if my precision was a tiny bit higher on disease, but I'm actually really happy here. This is not bad. Yeah, I haven't changed a single thing about this logistic regression, and it might be actually the best one. Again, 90% accurate. None of these values stick out as really low. Both of my classes are about evenly split with these metrics, so neither one is higher than the other by a huge margin. Again, my precision maybe sticks out, but not too bad. My confusion matrix, I'm not getting a lot wrong, which is nice. And the one that I really want to make sure so I know instinctively I want to make sure that no one is passing by and I'm missing their heart disease. That's just limited to 2, so that's not too bad here. When I'm doing a classification problem, and by me, I mean me personally as Emily Dale, I always go logistic, decision tree, random forest. If I'm feeling fancy, I'll go with a support vector machine. I threw that in this semester because I thought they're interesting. I honestly really wanted to show you the StatQuest video because I loved it. I thought it was just really, God, the statistics behind it just blow my mind. But this week, partly what I really wanted to focus on was, this is how it works, is that you're not going to always know, oh, I need a decision tree for this one, and that's where I'm going to stop. It's about the process. It's about trying things and going back and revising them. If you're part of the Crossroad Classics Analytics Challenge, or even if you're not, one of the things they're doing is that they're having people try out models up to 5 a day and submitting them for this challenge. Homework 2, I believe, is the Titanic one. Maybe it's homework 3. That is another challenge where people are trying out different models and submitting their scores, because there's no such thing as one absolute best model. We're all just trying the best that we can and trying to figure out what's the best possible combination of variables. All right, with that, let's go into decision trees. We've done this before again, so I'm going to go through pretty fast. Decision tree. Ooh, accuracy is a little bit lower. Okay, 78%. Let's see how we're doing here. Okay, I'm seeing the issue here. Both of these kind of peaked up a little bit. A couple more wrong here, quite a few more wrong here compared to the logistic regression. And then this is what I meant by the scores being just really off. You see where this precision score is very nice up here with no disease, and then heart disease just plummets to 69%. This is what we don't want to see. We don't want to see that huge discrepancy between the two classes. So just me, as I'm looking at my my evaluation metrics, that points out to me, hey, something's not so great here. This is just so you can print your decision tree. You won't be able to see it here as well, but it does print out a nice picture to your files, and you can open it and zoom in. But yeah, that's how you can see what it actually printed out as the different classes. And when you zoom in here, it actually gives you those cutoffs of here's the variable and here's, true or false. This is kind of how you follow the pattern. And then, of course, decision trees. We don't always use decision trees because they give us the absolute best metrics. We use them because they have really great features like feature importance and helping us walk through how do you get to that heart disease, what kind of decision points, and in this case, what are some of those red flags we should look at with people that might get heart disease. So in this case, it's looking at that CA, which is number of major blood vessels, okay. CP, which is something, okay. Again, not all of them are defined, but we could look into that a little bit further here. So that CA, number of major blood vessels that are uncovered during that fluoroscopy, old peak, I think that's that ST depression. So all of these are the most important features. A little bonus feature for you is hyperparameter tuning. So far, we've been doing this very manually and just saying, okay, what if we try this? What if we try this? There's actually some really cool methods to try a lot of parameters at once, and that's hyperparameter tuning. My favorite one, just again, for me, is grid search, because I like saying, hey, try these 15 things and tell me which one has the best accuracy or the average precision. So what this is doing is saying, I'm going to send you a model, and I want you to try a bunch of things. So try a max depth of 3 and 5 and 10 and 12 and 15. And what about if the minimum sample split is 2, or what if it's 7 or 10? And remember that criterion. What if we did Gini, or what if we tried entropy? Try it both ways. So it's going to go through this grid. That's why it's the grid search. We're going to try 3 as the max depth, 2 as the minimum split with Gini. And then it's going to try 3, 2, and entropy. And then it's going to try 5, 2, Gini, 5, 2, entropy. And it's going to go through all of these combinations, and it's going to create your model. And you can specify what you would like to basically aim for. In this one, I just said average precision. You can say accuracy. You can try a bunch of different things. I have a couple of articles up here that point you through. But when I run this, it's going to tell me exactly which parameters I should do. And there we go. So it tells me the entropy criterion with a max depth of 3 and a minimum sample split of 2 is my best bet. So let's try it. And you'll see actually over here, this changed from earlier, which tells me that there's a little bit of randomness here. I didn't set my random state right here. Um, so yeah, this tells me that there's maybe some randomness here, and that the minimum sample split isn't actually doing a ton here to um, make the average precision as best as it can optimize. That's the word I'm looking for. It's not optimizing it much better than other options, since it's not super consistent, but it at least gives us something. And so when we run this, you see we get this. Um, and if you compare, and this is where it gets hard when I have a wide screen but not a very tall monitor. We can compare. So this is my base decision tree accuracy of 78%. My worst precision was 69%. Down here I have accuracies up to 80, my worst precision 71. So it gave us a little bit of a boost. Nothing crazy. It didn't make the model go from 0 to 100, but it gave us a little bit of boost. That's what the hyperparameter tuning is really doing. It is not the first step you should take. It's more of I have an idea of the model I want to use. Let me just make it the best possible. So we've got our decision tree. We've got some good ideas of what's working. Let's try a random forest classifier. I'm not doing the hyperparameter tuning on this one because I figured out it shut down my computer. I tried to hyperparameterize too many things. And this is my best one for this one. I tried a few things, but 88%, it is getting better over here. You see the classes are a little bit better. 88%'s about the best accuracy I got, but the logistic regression is still just killing it. It's doing great. And then finally, support vector machines. So the documentation, I have it open right here. We're using scikit-learn still. We're using SVC. So it's a C support vector classification. And then you'll see all of the parameters you can use here. Part of it that's a little bit tricky is that you do have to specify the kernel, and the default is the RBF. So if you go down, I believe it's on this page. On one of these pages, it tells you what all of these stand for. It's somewhere. Anyway, okay. Oh, there we go. Radial basis function kernel. I found a few different tools that have helped me with this. Honestly, the ones I've seen so far, the RBF is good for complex nonlinear relationships. So if you think it's nonlinear, go with that. It can be sensitive to overfitting. Everything I have seen has said to start with linear, but try a few things out. Everything I have seen and used and witnessed with SVMs is that they work really well if your classification model is already working well with decision trees and random forests, and it's giving an extra little boost. But if it's already working well with maybe logistic regression, there's a chance this one might not be the best. But let's actually try some stuff out and see. So I'm going to import it. I'm just going to do the basic one. So this is with RBF. And yeah, you see it's actually pretty bad. My accuracy is 67%. These just tank. It cannot determine heart disease versus no heart disease. It's miserable at this. So first take at an SVM is just not a great one. But if we do linear, and that is why I was kind of thinking to myself, like, this doesn't feel like a linear problem. But deep down, that kind of makes sense, right? Because logistic regression worked best, and the math behind the logistic regression gets us down to a linear regression. So maybe that makes sense. And even, let me see, what are some other ones? Like, I can try poly and see if that works, because that kind of fits more in my head with the logistic. But no, the linear just works so much better. I'm going to save that one. Um, but yes, this one again, I have not used it as much in business because if you look at this model, compare it to your decision tree, compare it to your logistic regression, this is much more difficult to explain to someone else. Now, you can explain the theoreticals, you can probably explain the math. Again, that video from StatQuest is just phenomenal at that part. But actually explaining what what criteria is this model using to separate the two classes, that's where this gets really funky and it's more difficult to explain versus logistic is kind of more self-explanatory and then your decision tree gives you, again, it's not the most accurate model, but it gives you some pointers on how to explain it to people. That's where these business problems keep coming back to. I was about to say haunt you, but really to help you out. Um, a lot of data scientists go for these SVMs, for neural networks, for all these fancy things because they sound cool. I'm telling you specifically, don't do that. Um, Try them out because it kind of gives you that pat on the back of you tried it and you're still seeing the simpler models work better. Um, but a lot of times businesses don't want you to do these fancy ones because they won't work as well or because you specifically can't explain them as well to others. Now to wrap this up, scaled data works about the same with the linear model. And there's another scalar you can use, which actually worked a little bit worse. But yeah, we go back to it. And the big thing to know in this module is SVMs are genuinely really cool. They're fascinating to look at. I like studying them. Sometimes simpler is better. When you're doing a classification model, I would honestly recommend start from the first model we use, start with logistic. It's not always going to be the best one. I have found almost all of my models, random forest will become the best model. In this case, we got close, but logistic was the best. Except this one actually got pretty close. Now that I look again, what were those precision scores up there? Let me take one last look. Ooh, actually, I might have to take this back. We actually did pretty well with that SVM at the end with scaled data. Um, but then that's where you come in with, can you explain this to someone else? That's going to be a lot more difficult than explaining a logistic model. So then you come back to, is that tiny bit of lift you get with the precision and recall worth the black box, the kind of the bit that you can't explain to other people versus logistic regression where it's a little bit easier to explain and implement in a business environment. So hopefully that helps as you walk through some of those other problems. This is truly what I go through every single time I get a new problem, new idea. I walk through these steps. Some of my other tips, so I'm going to drag this over. These are all the notebooks that are running right now for me. I highly recommend you have some of these open. So like, let me open up module 1. If you need some code from here, copy and paste it in your new code over here. You should not have to memorize a lot of this code. You should start to recognize this for sure, but you do not need to memorize code. You can have this open and go back and forth. Have the documentation open. I try to leave different hints in here and links and things, but have the documentation open and really try to dive into this. Dive into the data documentation. Again, I was telling you I don't know anything about some of these things, but the people that made the data, they do. Oh, nice. We were pretty spot on. Logistic was working better. Except ours was actually pretty good. Ours was way up here. And then the resources I've been sharing with you, those are the default ones I always go to. I love Geeks for Geeks. DataCamp has some good solid ones. I occasionally post Medium articles, YouTube videos. The YouTube ones are the ones I have said I fully approve. I like these. The Medium articles, I try to pick the ones that are pretty Don't go into a ton of detail because pretty much anyone can post those. So just be careful on Medium because, again, anyone can post them. But I think that's it. I think I'm done rambling. Hopefully, this helps. Have a fantastic week, and I will see you next time. Bye.